All right, we're going to talk about maintaining the bottom line by reducing energy cost. And just to tell you how this presentation has gone, my first stab at the title was minimizing the bottom line by reducing energy costs. And I looked at that and I said, that didn't seem right, minimizing. So then I put maximizing, but actually the title of the program is maintaining. I like the term maximizing better, but we'll go with that. All right, so let's talk about energy efficient swine facility. Greg mentioned I worked at the University of Nebraska, and that was a long time ago. I mean, we're talking in the middle 70s. And this was the first building I cut my teeth on with Bob Fritchen. Was this guy right here, the modified open front. No fans, no heat, just purely energy efficient barn, okay? And if some of us are old enough to remember the 70s, we had the oil embargo. We had a lot of things that were restricted. We actually had gas lines that were out of sight and all that. So the one thing on my first building project was to add insulation so we could retain body heat. And if you look at this, again, a very energy efficient type construction. Now keep this in mind because at the end, we're going to talk about the future in building design. Not necessarily this concept, but possibly some components of this building. All right, so energy conservation. Why do we even care? All right, I mean, what is the point here? Again, I think we can anticipate higher energy cost. There may not be enough energy available to meet demand. I'll give you an example. In South Dakota, we're sitting here by the year 2015. We're going to be 800 meg short. Okay. The people in our East River, our rural electric co-op, said that we need to have an 800 meg worth of power by 2015 to meet the demand. Now, ordinarily, we like to see that come up in a coal-fired plant because coal still is the cheapest energy source. Unfortunately, with environmental, we already had a 600 meg at the Big Stone power plant. They backed away from it. And part of it was, the fact of environmentalists, etc. Third thing is because it's the right thing to do. Now, again, we can talk about, touchy-feely things here and being the right thing to do. But really, at the end of the day, we want to maximize the bottom line. Okay? When we save energy, we're improving that bottom line. All right. So I'll give you a couple examples. Okay, we had a South Dakota producer reduce his energy bill from $97,000 to $40,000. Okay, he had a 1,500 south fair to finish operation. How did he do it, or how did he tell us how he did this? Well, a couple of things. First of all, he gained a better understanding of ventilation by attending the workshop. And this is kind of a segue for me to promote our ventilation workshops. We have two different workshops. We have the basic workshop. We go through, the environment as well as, the basics of ventilation and troubleshooting. And then we have our advanced workshop where we get into more sophisticated control type stuff, more troubleshooting. And then we send out hobo units so that we can get an idea how your facilities are working. The other thing is he changed out controllers. When I go onto a site and that producer does not understand that controller, either we're going to gain an understanding of that controller or we're going to change it out. Okay? And we changed out a number of them in his swine nurseries. There was no way that control system was going to, or they're going to gain an understanding of that control system. And I asked him the other day, what else did he do? Well, he put bubble wrap on the north side. Now, he didn't do it necessarily for the insulation value, but he did it because it helped seal up the north side. He had double curtain-sided barns. Okay, another example is a unit that I work with. Last year, their 1 year's propane use for 2,400 pig spaces was 1,400 gallons. Okay, now they have September fill and a March fill, which again helps. But let me show you the next example. Here's the same thing, 2,400 head unit. He's got a September and March fill, wean to finish, single stock. Set up for 10,000. He used 10,580 gallons of propane. Okay, he realized that he had a problem. Okay, this particular individual, and really, I think the bottom line, what happened here was that he had The control setting was set for double stock, so he had increased his ventilation, but when he went back to single stock, he was moving moving way too much air. So again, $6,900 a year extra. Okay, so what is normal? Okay, what is normal? I just showed you extremes. One guy's using 10,000 gallons, the other person are using about 1,400 gallons. Again, we look at average and we use FinBin from the University of Minnesota. Again, wean to finish per pig, we typically, from 2004 to 7, $1.43, 2008, $1.50. Finishing pig, again, for finishing pig, about 0.71, 2008, because of the higher propane costs, we were at $1.08. In Iowa, the rule of thumb that Jay Harmon uses is 2 gallons of LP per space per year for wean to finish. Okay, so if we look at a 2,400 head, on the average now, we would be at 4,800 gallons of propane use. Now, when I make the equivalent now, there's about 91,600 BTUs in a gallon of propane. So you multiply that out with the 2,400 head, that's 440 million BTUs of energy. Now, the question is, can I cut that energy use? Now, the gentleman that had the high energy bill, he was over 1 billion BTUs of energy. So you got to look at it and say, okay, where can I cut and not affect productivity? All right. What are the common causes of high energy? Again, controller settings, and we'll talk about that a little bit later. Variable speed fans, the bandwidth, the percent settings, our furnace off settings. We look at equipment sizing, fans, furnaces, our winterization program, emergency thermostat, and preheated hallways. So when I looked at it, I says, okay, so how can we save energy and reduce cost? Okay, first of all, it's going to start with good building design and construction. Okay, it's going to start with good ventilation system design, and then after that, it's overall operation and management of the system. If you get those 3 things going for you, I can pretty much guarantee that you're going to be successful with your operation, but you got to have the basic components to make this thing work. All right, the idea now to retain or reduce energy now is to utilize the pig's body heat as much as possible to keep that building at your particular set point temperature. Now, majority of the heat lost in a ventilation system will be through the exhaust air. So approximately 80 to 90% of your heat is really lost to the ventilation air that's exhausted out of the building. Now, we have to be careful that we don't cut that too much, otherwise we're going to end up with air quality problems in the unit, namely high relative humidities as well as high gas levels. Insulation, again, important. So, again, what we're trying to do is utilize the pig's body heat and then balance the system out. All right, so we look at heat production in growing pigs. And this is a graph put together by Dr. Mike Brum. But when you look at the heat production, this dotted line is the old heat production line. Tammy Brown and her counterparts at the Mark Center, Meat Animal Research Center at Clay Center, Nebraska, have come up with this curve for the new genetics. And we're thinking actually this is almost old, or it is old, and that the curve is a little bit higher yet. So what we're saying is the new pig, the new genetics, is actually producing more heat, putting on more lean gain. Consequently, it results in more heat production. So when we look at, for example, we're sitting at 176 pound pig basically, we're about 700 BTUs of total heat, or sensible and latent heat energy. Okay, this is sensible heat that we use to keep our building warm. Latent heat is part of the evaporation process. All right, so let's look at building design and construction. Okay, we'll talk about insulation. Again, building materials, using good building materials to keep things sealed up, sealing unplanned openings, curtain installation, attic air intake, and lighting and heat lamps. And I'll just talk a little bit about lighting. Most of the facilities I go in today have compact fluorescent bulbs in them. So that's great. I mean, Alliant I know has rebates for those types of bulbs, and like I said, you guys, as far as swine producers, I think are ahead of everybody else as far as using compact fluorescent bulbs, because every unit I go into, especially on new construction, are using those bulbs. Now, in heat lamps, the research done by Hung Wei Shin from Iowa State indicated that we should look at 175 watt bulbs. Again, the savings over a 250 watt bulb, it can be substantial, again, depending on your size of operation. I think they estimated roughly about a $5,000 savings. So again, line, if you're looking at rebates and that type of thing, there's some opportunity there. All right, so let's look at insulation. And first of all, most of these facilities are built usually between R30 and R40. Okay. If you're at, say, R20, I would recommend you at least get it up to an R30 insulation. 10 inches, 12 inches of attic insulation. The walls, 2x6 wall construction, combination of the other materials, R20. Now, the area where we can pick up probably our greatest savings and heat loss would be on the concrete walls exposed to the outside. And again, where we'd be looking there is perimeter type insulation. Balance point temperature is the outdoor temperature at which energy losses from the building equal the energy gain in the building. Okay, so when it's colder than the balance point temperature, and supplemental heat is required to maintain the indoor temperature. All right. So if it's colder, say for example, if we come up with a balance point temperature of 32 degrees, anything below 32, we would need to add supplemental heat. Now, when I looked at, the amount of hours in Des Moines, Iowa, I think I came up with roughly 3,000 hours below 30 or 32 degrees. If we're above the balance point temperature, then you have the heat production from the animal, lights, equipment, pigs, the solar heat gain maintains the temperature at above the indoor design temperature. So, of course, as it starts to warm up, then we need more ventilation. This is a very important term. And you can take, somebody to come in and analyze your building and look at your insulation levels and look at what you're doing with ventilation, come up with a balance point temperature, and then you can tell when those heaters should turn on, when they should shut down. All right, so getting ventilation set right. I'll give you an example here. We were looking at an R40 and an R19 wall versus an R30 and an R3 wall. When we look at balance point temperature now, say for example on a 25-pound pig, we should be about 2.5 CFM per pig. Okay? The balance point temperature now at R40 and R19 is 10. So anything below 10, we would have to add supplemental heat. If we had an R30 or an R3 wall, we'd be at 22. However, if we have 5 CFM per pig, if we're over ventilating, now all of a sudden our balance point temperature goes to 41 for an R40, R19, and then a 45. So what this points out is still ventilation, even though we're poorly insulated, makes a huge difference of when supplemental heat will be added to the building. So when we look at uninsulated concrete walls, and especially in weeding to finish, a 6-inch concrete wall has an R value of about 1.33, okay, resisting. So if we have a 0-degree outdoor temperature, we're going to be looking at a 70-degree room temperature. But if we add insulation, 1 inch of insulation or rigid insulation, that R value goes to 6.33, and then all of a sudden our surface temperatures are 62. Why this is important, especially on weeding to finish, is those pigs radiate heat to that wall surface. Okay, and you want that wall surface as warm as it can get, and also the fact that we're slowing down the amount of heat loss. So if you already have an let me put it this way: if you got an R30 ceiling insulation and you got an R20 wall, don't add any more attic insulation. Look at perimeter insulation. You'll get the most value for the money spent there. All right. Again, I'm going to just show you some things in building construction that can really horse stuff up. And we look here, again, cross-section of fan transition. This barn was really quite nice with the exception of this. Again, we were looking at fan capacity and dividing that by 400 feet per minute. Again, ideally, if you looked, again, 8-inch, we had 1.67 square feet of opening. Ideally, we'd have 15 square foot, which is a little bit impractical because you do have to have some manure capacity in that pit. But the minimum really should be about 7.5 square feet. Why am I showing you this? Because when we look at energy and we look at fan performance, if we start restricting airflow right at that point, you're not going to get the amount of CFM per watt that we're trying to deliver with the system. Another thing that we constantly have to work with, and that's attic air intake. All right? And this, what I'm showing here, happens to be the proper way to construct a system, where, in other words, we have an 18-inch overhang in this particular case, 9 inches of solid, and roughly 9 inches of opening. Again, that opening depends on how much airflow that we're going to be bringing into the attic space. All right, so this is the equation. We look at attic air intake, total hot weather ventilation, and I never deviate from this whatsoever. Divide that by 400 feet per minute. Said another way, 1 square feet of opening for every 400 CFM of airflow. So if you're pulling 60,000 in that barn, you need to have 150 square foot of net free opening, which is a minimum of 3/4 inch by 3/4 inch. Okay. So in other words, a 200-foot long barn, we would need a 9-inch eave on one side. If you have this particular condition or situation, this is not good construction on the south side of a barn especially. And unfortunately, I was there because, again, his curtains were opening up too quickly. And, you know, again, you look at the balance point of that particular facility, it was probably in the 40 or less than, yeah, probably in the 40-degree range roughly. That producer still hasn't changed that out yet, and that was about 8 years ago when I looked at that. So that's wrong. This is definitely wrong. And so, again, this is what happens. All right, the other thing on construction that we have to be well aware is the insulation stop. Even though we have 9 inches of opening, we got to make sure we maintain a 9-inch clearance above the plate line so that air can flow freely into those interior inlets. Okay. Again, if you don't, you start choking that off, you affect fan performance, and you start running more fans than is necessary. Okay. Curtains, again, we recommend on curtain openings, again, getting back to construction, is a 3-inch run-by here. Is the proper way, and actually what we're showing here, this is, we were able to develop about 0.15 inches of static pressure in that facility. Now there are some other issues there, and you don't want to develop 0.15 either, but again, the point was that curtain, you can make those buildings tight enough with a curtain facility. 2-ply curtains. Again, we look at infiltration, unplanned openings. We look here at curtain overlap of 1 inch, 2 or 3 inches. Again, if we're less than an inch, for example, per every lineal foot we're going to get about 100 CFM per lineal foot of air opening. Say, for example, with a, let's see, that one would be a 30-mile-an-hour wind. Let's just go down to a 10. You get about 40 CFM per foot. So if you're depending on your air inlets, but what happens when you're trying to ventilate a barn with a curtain, during the cold weather, you're going to see up and down on your temperature. I mean, it's extremely difficult. And that's why in today's barn, when we build a barn now, we recommend at least 45 CFM per pig for double curtain sided barns, and up to 60 CFM per pig actually for tunnel ventilated barns to pull through the inlet. So once that, again, the temperature gets high enough, we really don't care. But when it's 30 or less and our curtains are still opening, we do. Again, difficult. So anyway, the overlap necessary minimum of 3 inches. Again, the slightest crack served to over the ventilated barn. Very little difference between either a 2-layer or 7-layer curtain. All right, so let's look at ventilation system design. We're going to look at fans, inlets, heaters, and controllers. And again, looking at a triple wide barn, the amount of exhaust fans in those facilities. This is a really important table. This one right here is the recommended minimum ventilation rates, and it's served me very well over the years. And you may disagree or agree, with some of these numbers, especially on the hot weather side. But when we look at the sow in a litter, again, 20 CFM per sow, and again, minimum rates, the two things we want to accomplish is maintain our humidity levels between 50 and 70%, and we want to maintain air quality. For example, ammonia levels should be less than 10 parts per million. CO2 levels should be between 2,000 and 3,000 parts per million. So that's the idea of minimum ventilation. All right. So again, we look at a nursery pig at 2 CFM, 3, and so forth on down the line. Again, hot weather ventilation, we get into our larger fans. And I guess the one thing I want to point out, we talk about breeding gestation here. Generally in that roughly 250 to 300 CFM is where we set those up. Again, this is a key one, that 120 CFM per pig. And we've had a number of tunnel barns that have not met that particular criteria. Static pressure. Again, you have to understand pressure and the resistance to airflow. And it was interesting when you look at that CFM per watt on a fan and how that changes when we have more static pressure in the system. When we purchase fans, for example, we're looking at no more than 0.012. It's where we like to operate. When we start looking at these systems, a lot of cases we're at over 0.12. We're at 0.15. And so you need to have a fan that can operate against those higher pressures. And here are the pressure points. If we do everything right, the air intake into the attic space should be less than 0.04. Your air inlet should operate from 0.04 to 0.1. Your transition should be less than 0.05. So just adding up, if I'm at 0.04, 0.06, I'm at 0.10. My transition at all of a sudden now I'm at 0.15 pretty easily. I did mention I do work on the filtration systems on the G and the bore studs. And again, what happens there, we're adding about another 1/10 of an inch of static pressure on these systems. Cool cells, usually a little bit less than 0.05. But the thing to remember about it is pressures are additive. Every time you have a choke on your airflow, that adds to the pressure that fan has to pull against. All right, so how do we, we're looking at CFM per watt. And I was looking at Alliant, and there, and again, there's some rebates for pork producers on, buying, better efficiency fans. Not sure. This is probably like a 16-inch fan, I'm guessing, somewhere in there, 14-inch maybe. But again, looking at the CFM, we talk about 0.05 to 0.1 is the range. Again, we're talking 8.5 to 7.7 on efficiency. The thing again is to look for, if we're at 0.15, though, look how bad that fan drops off. We're sitting at 3.5. So again, the efficiency is, in that particular unit is really bad. Here's a 52-inch fan. Okay. When we buy 52-inch fans, here, and this is a pretty good one at 23.8, some are a little bit higher than that. This one maintains its airflow rate and efficiency going down to 0.2. Now, I do have a rule of thumb, and it's an airflow ratio. What you do is take the airflow at 0.2 divided by the airflow at 0.05, and I'll take a 51-inch fan. You say 21,000 divided by 28. Our ratio there is 0.75. You want to purchase fans that are above 0.75 on the airflow ratio. And the better that ratio, the higher the ratio, the better that fan will perform against those higher pressures. Now this one is kind of interesting because it would qualify for a rebate here because of its 29.5 or 25.6. But look what happens when we start putting pressure on it at 0.15. We're down to 18.1. And our ratio here at 11.5, we got 9,900 divided by its 0.43. So again, not very good. So you really have to kind of look through the whole data sheet on these fans to make a determination on your purchases. And how I do that, there's a couple of ways of doing it. You can get the book, The Agricultural Ventilation Fans, or I just go Google and I put BESS fans, BESS fans, and Google it, and it comes up to the University of Illinois site, and you got all the fans that you need, off the internet. All right, cost of low efficiency or restricted fans. Again, 24-inch fan running at 0.05 for 8 hours a day, 6 months. You can see the difference at 8.7 versus 11.5. You could probably multiply that times 6. Just to kind of get you a difference if that fan was running all year. Fan selection, 24-inch, if you got the most efficient at 19 CFM per watt, $24 for that period. 8.7, $70. So, yeah, the 8.7 watt might have been $100 cheaper, but in the long run, that particular unit is going to cost you money. So, look at those efficiencies, those CFM per watts when purchasing a fan. Inlets, that's always the key. Now, you wouldn't think that inlets would have anything to do with energy efficiency. However, when you have inlets, different ones where you have, like, for example, this one, and the airflow is going up into the attic space instead of into the barn, you have a particular problem, okay? And so management of these inlets and having systems is extremely important to be able to control energy. Again, inlets opening up too far, we're allowing too much cold air into the building. We're not entraining that air, and this is where we look at a goal here. When we have airspeed coming in, we like to see that 800 to 1,000 feet per minute. So that we're driving that cold air in, we're getting a good mix of that air before we get an exhaust, and our air distribution patterns are where we like it to sit, where we like them to be. If you're just dumping cold air in, and especially if you're dumping it on a sensor, you're going to have some real problems with temperature fluctuation with that type of situation. Inlet management is important. Again, this particular case, it's a wean to finish barn. This operation would shut every other one off and just leave this one open when the pigs were really small when they came into the barn. And as they got bigger, they would open the back side. And the only time they ever had these side ones open here or here is during a summertime, hot weather, when they were in tunnel mode. Okay. Furnace sizing. Okay. Another issue here, we have BTUs per hour, CFM times 1.1 times your temperature difference. Okay. So, for example, if you're looking at a swine nursery, I would probably say 85 minus 15. We'd have a 100-degree temperature rise. Take it times 1.1 times the CFM. If you got 200 head in there, you'd probably be at about 600, roughly 4 to 600 CFM to size that heater. And again, you have to remember, as those pigs get bigger, of course, we have more heat production from the animal itself. In this case, in a wean to finish, we're talking 6,000 CFM. This is a 1,200 finisher double stock. We're looking at 7,000 BTUs. Take that times, again, the temperature difference, 82, yeah, we're at 600,000. So, again, remember the heat loss from the animal. You take that, you subtract that out, and then that sizes the heater for that particular ventilation rate. Furnace sizing rules. A furnace is big enough if it shuts off on the coldest day of the year. Okay? If it shuts off on the coldest day of the year. Okay? So if it gets down to minus 15 and it shuts off, it's big enough. Okay, the longer and also remember, the longer the furnace runs per cycle, burn cycle, the more uniform the heat distribution with the airspace. Okay? So if you got a heater now on these colder days that runs 100% of the time, it's not a bad thing. And you know, you may look on a wean to finish, depending on the size of pigs. We had one case where he actually had 200,000 BTU heaters in a 1,200 head room and was getting along just fine, versus the 500,000, which we see typically in a barn. Okay. And always, you know, we always ask the question, why do we have 500,000 BTUs worth of furnace capacity in the barn? What's the reason? For power washing. Okay. It has nothing to do with really, you know, the operation when there are pigs in it, but for power washing you do need that extra heat to help dry the barn off and those types of things. Okay. Furnaces and pilot lights, again, they do burn, and then the question here is if you keep your pilot light on all year, you're going to waste some energy at that particular point. So once we get into the warm weather situation, the message here is to shut those pilot lights and keep them off. You just have to remember to turn everything back on in the fall. Okay. Variable output furnaces. And this is where we talk about the blue valve. This guy right there. And I was just looking up LB Whites the other day, and for example, I forget what the model is, but anyway, they were at 250,000 BTU. If you turn that valve the right direction, you can cut that to 175,000. So once you get done power washing, it is recommended that you go to your lowest setting on those heaters. Okay, 100,000 BTU can cut it down to 50 and on the smaller rooms. But look at that valve and to see what position. It's not to shut the gas off, it's to reduce the amount of heat production from the heater. And the lower it is, generally the better. Okay. Electronic controllers. All right, so we got all kinds of them, and we get into trying to gain an understanding of how all of these different systems work. And some are a little bit easier to understand than others. And when we look at expectations for controllers, they do. I mean, for the most part, we can control and monitor temperatures well. Okay. Humidity control, I would not run a barn off of humidity control. Okay. There's way too much variation in humidity in that unit as those pigs get up and active during the day versus resting, and to run a barn off humidity control is not. If you're looking to pay a lot of energy, just put it on humidity control. Okay, that's kind of the message there. Drafts, again, very difficult to measure drafts, inlets, airflows, and like I said, most of the time, you know, it's temperature. Okay, and the other thing about humidity control is the humidistat or the unit, after about 6 months, needs to either be replaced or at least calibrated again to make sure that it's operating, telling you, you know, what it is. One of the major things that we run into is some of those controllers have not been changed the day the electrician left. Okay, and I'm not sure that you want your electrician or the guy at the factory that set the thing up to operate your swine barn. Okay. So you got to, again, gain an understanding of what those controls do. Sensors, again, this is just an example. Keep those sensors out of the streams, out of the heater stream, out of the inlet stream. So that's very accurate. I had a case, and if anybody's heard me speak about this, but where they put an LBY heater on top of this sensor. Now, it happened to be just a nursery on a solid floor and raised decks. So in their infinite wisdom, they put the heater on top of the sensor. So where does an LB White make up its makeup air? From the bottom. So every time that heater kicked on, it pulled the cold air off the floor, which lowered the temperature, which made that heater run, until it caught up. And we had temperature swings in that unit of 10 degrees. So what do you think his solution was? He couldn't keep up because his fans went off. The solution for him was a bigger heater, okay? And not necessarily that was the right one. Where 60,000, he went to 100, 110. So once we got that sensor moved, you know, then there wasn't we took care of the problem. So in a typical swine facility, what percent of heat loss is associated with ventilation? We say 85 to 90%. And one of the things we want to make sure here is you don't want to go home and reduce your ventilation because that could cost you even more. So you got to have an understanding of what your environment is within that barn to make sure that you're within the ranges. So overall operation and management. Of course, we talk about temperature. We look at settings. We'll talk a little bit about reduced nocturnal temperatures. Controller settings. We want to look at variable speed fans, the bandwidths, the minimum speeds. Setting your motor curves, the heater on-off settings, as well as maintenance, general maintenance. When we look at pigs, again, extremely adaptable. And again, when I got back to that original slide, about the modified open front, actually the Nebraska-style MOF, this is the thing that we looked at. What were the lay patterns, for these pigs? And again, looking here, they're warm. These guys are cold. Again, touching. We look at a wean to finish barn. These guys are chilled here, and again, too warm. And if we got our heater here operating, again, an indication of wasting heat here. Again, in this case, that they're comfortable. All right, so we look at the thermal neutral zone of where we want to operate as far as temperature. And again, the lower you maintain that temperature, the less energy you're going to use to keep that barn warm. And we always have a really not a heated discussion, but a lively discussion of where that needs to be. In the wintertime, we like to be as close to the lower critical temperature as we can. Summertime, of course, we're closer to the upper critical temperature. But when we look at recommended set points for the different ages of pigs, if we take a look at 15-pound pig, of course, we're talking about 84 degrees. And that's very common. But then we start dropping those down, 45 at 72, and so forth. 100-pound pig, we'd be at 64 degrees. And over 200-pound pig, actually looking on this side, we'd be in the wintertime, 63 degrees on a slatted floor, 59, 59. Now, how many of you run your barns at 59 degrees? I would say probably, we never have run, maybe one person I've run into over the last few years that have run them that cool. So, again, we have to look at, okay, how cold can we run it? Would reduce some of the energy use in a barn. Now, I have the students go through comparing 64 to 60 degrees, and it amounts to, let's see, the balance point temperature at 64 is 22 versus 17. So again, there is some energy savings, amounts to maybe roughly $1,000. So again, something to consider, but also performance. The other thing is temperature fluctuations. You look at temperature and how how it fluctuates, and here we got it fairly steady through. But if we're getting a lot of fluctuation where, especially during cold weather conditions, that's a problem. For weaned pigs, we want to see no more than 4 degrees fluctuation per hour. We want to have, there's limited data for finishing. Finishing pigs, of course, can handle more. Now, we do talk about taking on the nursery, fluctuating or using reduced nocturnal temperatures and knocking that temperature down by 10 degrees. And we're going to be looking at a study. University of Minnesota's got a grant, and we'll be redoing this research to see again with the newer pig, the newer genetics, because this is old data. This is actually back from 86, 85. But again, the idea is from 7 p.m. at night to 7 a.m. is to reduce the temperature in that room by 10 degrees. Okay. And again, the idea was to end up saving energy, which is what they did. Okay. So if we look at average daily gain, actually the reduced nocturnal gain was a little bit better. Feed intake, a little bit higher. Again, that was significant. Our feed gain was about the same, but we did use less propane in this particular example, and this is on an average of 4 or 5 week trials. So 665 gallons here versus 559. So it'll be interesting with the new controls and that type of thing, you know, how much energy we're really going to save going this route. This is why we don't want to control with humidity, because of this fluctuation. These fluctuations. You can see as we start monitoring it, and we say, for example, we're at 50%, then all of a sudden we're up over 75, back down. It's very dynamic. You don't maintain a level humidity in these barns. Okay, it goes up and it goes down. And again, the range 50 to 70. Now we had cases where the guy had his controller set, I think it was at 65%. Anything over 65%, he would start the ramp. Okay, the ventilation system would increase. What do you think that did with his heat bill? Increased it dramatically. So that's one of the reasons we're not very excited about using humidity or sensors to control ventilation systems, because of the dynamic with relative humidity. Okay. All right, so let's talk about ventilation controls. First of all, just to give you some basic background, I'm sure most of you we talk about bandwidth. Okay, and that's where the fan, variable speed fan, goes from the minimum to the maximum over a particular temperature range. Okay. Then we're also going to discuss, so if we look at a system now, a lot of them are set up. We have 2 variables, some cases 3, and then we have a number of single stages on top of that. So when we set the thing up, okay, first of all, we have our minimum right here, our minimum ventilation rate, and that gets back to that chart, 2 CFM, 3 or 10 or whatever the animal weight. And then we have a band ramp, and generally we talk about 2 degrees. It should be no less than 2 degrees. Okay? And if your fan is oversized, sometimes we go to 3. We go to a little bit more. Same thing in an offset. This bandwidth, maybe we could cut back to 1.5 degrees, and then we start staging our differentials as we go through, adding more fans. And this is how it works. Okay? If you look at a ventilation system now, here's a set point of 70 degrees. We have a 50-pound pig. It's a curtain-sided finisher. Right now, on that 50-pound pig at that 70, the balance point temperature there at 5 CFM per pig is 23 degrees. Okay. So anything below 23, we're going to have to add some heat. If that, by chance, was set at 10 degrees or 10 CFM per pig, we'd be at 45 degrees running. So again, as we start ramping up and in this case, we're going from 5 to 10 CFM per pig, and a lot of our variable speed system or fans are set up that way. You can see, and so what happens here, if we're off on that setting, we can start generating a lot more or wasting a lot more heat, because that's a tremendous difference here, temperature-wise. Again, we added more CFM to go to 15, and it's 54, 61, and then what we're always starting to do is remove heat out of the building. Wintertime, we don't necessarily want to remove heat. We want to conserve heat. Let's look at a bigger pig. If we were running at 5 CFM for this 150 pig, minus 27, there would be enough heat production in that building, in a halfway decently insulated building, we could get down to minus 27 without adding heat. That's probably a little tight. Normally we'd run about 7 CFM, and so we'd be somewhere, maybe around 0. Okay? In this case, if we were at 10 for the 115, then the balance point temperature is 14. Okay, we add 15, 31, and so forth as we go through. So the bandwidth recommendations on stage 1 is 2 degrees, and that puts time, so your ventilation system has time to react. We run into guys that got them set at 0.5 degree, and there's no way that we can be that fine and to make sure that we're not wasting any additional heat with that system. Stage 2, 1.5 to 2, because again, when we go into stage 2, we're cooling that barn off. Now, if we're going into stage 2 when we should still be in stage 1, then you really have a problem. And that's what happens with these shorter bandwidths. We end up adding where the controller can't act quick enough. Okay. All right, here's another one. Heater offset. Okay, establishes a new basis for heating. And I like the terms heater on and heater off. It's easier for me to understand. If this is the case, now the rule of thumb is if you look at your high temperature for the day during a cold weather situation, you should always be below your set point. Always. You should be 0.2 of a degree roughly below the set point temperature. You should never reach it. Okay? Never reach it. So if you start on a cold day and you end up over here, you're wasting heat at that particular point. So the idea now is your heater on temperature maybe 2 to 3 degrees below your set point, and your heater off, and again, this depends on your size of heater. The bigger the heater is, the more oversized the heater is, the greater this offset needs to be. Okay? So if you have a wean to finish barn and you're cranking, 250,000 BTU furnaces, a couple of them, you're going to need a bigger offset, and maybe in the 1.5 to 2, so you do not overshoot the set point. Okay. All right. So here's an impact on furnace offset. This happens to be a nursery, but when you look at it, again, here's your temperature here, and this is the heater runtime. Okay. Furnace on at -2, furnace off at -1. Okay. We made the adjustment by taking that furnace off at 1.5 degrees and literally shut the furnace off at that particular point, just by making a 0.5 degree change in the unit. Okay. Heater offset, it's 1.5 degrees below to ensure the heater is off and the first stage's fans are functioning. And you don't want those things to ramp. All right. Variable speed fan rules. Number 1, 50% speed does not equal 50% CFM. Okay? So if you're at 50% CFM, you need to be roughly at 65% of the RPM of the fan. Okay, if you look here, and this happens to be a 200, roughly to about a little over 1,200 CFM fan. For example, if we set at 1,000 RPM, that fan now is delivering 400 CFM. Okay, and that's kind of at the lowest setting on those fans, is where which is 65% of the RPM. If you know what the RPM is, you can set your minimum speed from that rate, and hopefully you got fan data that will also relate what the RPM to the CFM capacity. Number 2, 50% voltage does not equal 50% CFM or RPM. All right. So you can measure the voltage, but for every fan motor, it's going to be different. So when we look at a 24-inch fan, we look here, we got setting up at 0.05 inches of static pressure at 230 volts. We're a little over 7,000 CFM. We cut the voltage to that fan to 120 volts. We're less than 2,000. Okay. So every fan is different. Okay. So you have to understand what the motors are to be able to set that minimum speed setting right. Okay. Number 3, every motor reacts to voltage differently. Okay. So if you may have a fan that you already had, feel really comfortable. We've had cases where guys will come out and change out a fan motor, and they say, "Oh man, this doesn't work at all." Again, because you got a different make of motor in the system. And I'll show you why in a little bit. All right, fan response to voltage. What you see here's a AP 24F fan. Here's an Aerotech, another AP 12-inch fan. Okay. If you look at the voltage here on that AP12, you can see at 110 volts, we're roughly at 40%, or a little bit over 40% at full RPM. But look what happens now in that fan when we're at 140 volts. We've just changed it, only the voltage here, by 30 volts. We've gone to 40% to darn near full within that small range. These, we like to see linear relationships, and the only fan size that gives us a linear relationship, or at least close to one, is the 24-inch fan. Here, this one. Okay? So, but, again, as you add more volts, then this fan increases pretty much, reacts linearly to voltage, whereas the smaller fans, and this is where we really run into the trouble, don't. And having the wrong motor curve is really critical here. So we look here. If we go from 107 volts, we're at 50%. We're at 132 volts here. We're at 50% on the let's see, which one is it? On the AP, the 24. So again, different voltages, fans react differently. This happens to be a prudent fan, PS12. This is what we use in our ventilation model. But again, we were in a 110 volt system. Within 110 volts on that 115 or whatever volt system, we went from 700 RPM up to 1500 within a really small range. Okay. Rule number 4, minimum speed not less than 50% RPM. Okay. Which is about roughly 40% of the fan output. Okay, minimum speed, not less. So if you got a 1700 and some fan, 850, 900 is really as low as you want to go with that. Okay, most fan motors are totally enclosed. Threfico controllers, 40% minimum speed when the motor curves are correct. The Vetrum never go under 24. So again, all these controllers, we always have different modes of operation, and Threfico makes a number of the control systems out there. So those are the ones that we're probably more familiar with. Okay. All right. Rule number 5. Almost every controller controls variable speed by changing the voltage. And this is true. Velcro's the exception. One thing about fans, and I work with the dairy industry a little bit, but variable frequency drives. We're seeing more and more what we call VFD, variable frequency drive motors, and they are they're much more efficient operating than what we're dealing with our fans, but they're also more expensive. So I know about, maybe 10 years ago, we were actually talking about that for the industry, but it never really caught on, and I think part of it, of course, was the expense. Okay. Motor curves. You cannot, on some of these control systems, they have motor curve function. Now, this really looks busy, and it is, but that's what is inside your box. Okay? Your control system has 10 different, on the Threfico controllers, we have 10 different motor curves. So if you look here on 60%, for example, 40% scale, you can see the voltage output, how much that changes between all the different motor curves. Now let's look at the Airstream, we'll look at the expert controller. Percent scale. At motor curve 1, we'd be at 125 volts. At motor curve 9, we'd be at 111 volts. So you can see how much these voltages change. Now in the 24, the AP24, we'd be at 146, roughly, give or take, a few volts here and there, depending on your power source. But again, and as I showed you before, these motor curves, or the motors react differently to voltage. So you have to remember that, and you have to make sure you have the correct motor curve for the fan that you're trying to operate, and also set the minimum speed. Okay, you look at a small fan, for example. Look what happens here on motor curve number 9. remember that fan responded really quick to changes in voltage. But if you have motor curve 9, you can set that at 50%. You go up to 113, 116 at 17, 119, and 123 at 90%. So when you start partitioning this off over the bandwidth, how that fan reacts, it's really flat, okay, until you get to about 0.2, 0.3 of a degree below on your ramp length, okay? And then it takes off. So if you have a heater overshoot by a 0.5 degree, it's not that much of a problem. However, if you're sitting here with motor curve 4, which a lot of these smaller fans were set up on, all of a sudden now I'm down to 40%. But look at 128. On that particular one, I'm going to be percent scale at 90% already. Okay? 90% of my capacity. So if I got a 1,000 CFM fan, I'm moving 900 CFM, and I got 200 nursery pigs. I only need to be moving 4. I'm moving twice as much ventilation air as I need to move by having the wrong motor curve set up. Okay, so it's real important. I mean, that's the one thing, and it is confusing, and I understand that, but you really got to sit down now. The fan companies, Airstream, Aerotech, Apney, they all have recommendations for the different fans on the motor curve number, whether it's 1 through 10 on those units. And where do you do it on the Airstream? On the TC5, for example, if you look at this button right here and you punch it, I think 3 times, is that correct? And it'll come up with TYP, okay? And then you can sit there and adjust your motor curves from 1 to 10. But you got to have the table so you get the correct motor curve for your fans. This one, the phase-on controller, is proportional, and there is no motor curve in that particular unit. So you're somewhat at the mercy of just trying to figure out where that voltages are, given the percentages on the controller. Supra, which is a phase-on product as well, do have motor curves, some motor curves in their control system. Verifan, and I need to check them out today because I think they have actually developed more motor curves within that system. Could be wrong on that, but all right. So again, bandwidth 2 degrees. Make sure you got the correct motor curve because if you don't, a lot of cases we're going to be wasting a lot of propane. Now, modeling heat loss or heat flow, Mike Brum, Dr. Brum has come up with a table. And again, what we're looking for here is the amount of estimated gallons of propane given pig weight and given to make sure that the estimated furnace efficiency at 95, furnace turns off minus 2 degrees relative to set point. And you can see, all right, for a 100-pound pig at 10 degrees minus 9, which means there is no heat needed. At zero propane use at minus 10. So again, what we're showing here for a 200-pound pig, we can go less than minus 15 and still not use any propane in those units. So again, again, it's a guideline. There's not exact science here, but at least it gives you a rule of thumb as you look at your pig weights. If you're running furnaces when those pigs, and it's 10 above 0, and you got 200-pounders plus in there, you shouldn't be really adding any extra heat because you got enough heat production from the pigs to be able to keep up. Preheat hallways. Used to design a lot of that. It was a nightmare to manage. And part of that reason was this. We look at Farrowing house balance points. CFM per crate, 24. That preheated hallway was 44 degrees. Okay, in other words, then we wouldn't have to need any more supplemental heat in the room at 25 CFM. What did I say before, though? The rate on Farrowing rooms is 20 CFM. So right away, we were already moving excess heat. We're at 35 CFM, then the balance point was 48. And if we ran our hallways really warm, which a lot of them were, at 51, then we had to up that to, from the heat from the south to get rid of it. We had to run 45 CFM, twice as much as what was necessary. Okay. The same thing, holds true on 1,200 head rooms. Just to give you, idea on balance points here. Stage 1 variable at 5, we'd be looking at pig weight 23 minus 4 27 on down. Go to 10 CFM per pig, you can see what happens on our balance point temperatures. All right, maintenance. Again, it's just a matter of, keeping things clean. Pit fans, as these fans and everything the pits get full, you can tell that this fan is not, we're not getting a lot of ventilation through that system. 1 foot minimum is what we're looking for. Okay. Between the bottom of the beam and the liquid level, we always want to maintain at least a minimum of 1 foot. Keeping the older fans, a lot of these have self-adjusting tensioners on, but some of the older ones don't. And what this shows is the fact that as this was the best lab data, this is where he was at, and after he adjusted his fans, he increased the flow. So again, it's just a matter of maintenance to keep these fans giving you the best. So are we sitting on time? Okay. Curtains, 2-degree bandwidth, 2-minute cycle time, on curtains. We want to avoid this situation where we're going down to 60 degrees and then back up to 68 and then back down, up and down. Look how much that on that particular facility. Okay. What's wrong with that picture? Again, maintenance as far as the amount of cracks and everything around the fans. Openings, 12% of the pit air was coming really through that particular slot there. Gaps, unintentional openings. Dirty shutters, 1/8 of an inch, 40% fan efficiency. All right, we'll finish up with just a little bit here on research in the future. Again, a couple of projects. One is reducing the environmental footprint of swine buildings, green barn designs. And to give you an idea, I showed you a partial slat facility. We're actually part of this green barn design going to look at it again on partial slats. Now, you may want to shoot me, because if you remember some of us with the jackhammers trying to clean those pens out. So we have some issues on how to hopefully solve that. The other thing that we're working at South Dakota State is a building design cost to reduce energy emissions by cleaning and recirculation of room air. This box right here signifies a biofilter in there, as well as we're starting to look at geothermal as a possibility to keep that air cooler, okay? And the idea here is we got, on tunnel ventilated barns, we got a wall full of fans. What we're trying to do is really reduce the amount of fans that within the barn by keeping that temperature cool. Now, I'll show you an example of that here. This is a barn up in western Minnesota, and it is a geothermal barn, ventilated barn, okay? It's a farrowing breeding gestation, nursery type barn. 800 sows. I'll tell you the cost. The cost in this facility was $800,000, okay? $1,000 a sow place, Okay, what you see then is from the wells. There's 300 wells dug, 280 feet deep, okay? And that water then is circulated through these tubes, these green tubes. You can see them. I forget how many they had in there. But the thing that's intriguing about this is they're going to ventilate this with this single fan, this 20 crate or whatever farrowing room, as well as nurseries with these one fan. Rather than having multiple fans, they're going with one single fan. Can they recapture $800,000? I don't know. I guess we haven't run the numbers yet. But, it's kind of intriguing, the thought. And I've had other people ask questions about geothermal. Can we use it in our pork production systems? And I don't know the answer to that. But I think it it's worth investigating, and that's what we're doing. Okay, you think you got energy use? These are the new cross-ventilated dairy barns, and there's 80 50-inch fans in that barn. It's 400 foot long. It's 80 of them. There's 800 cows. So, and we've done a ton of these up in the upper Midwest, and it's interesting. I mean, we've had the natural ventilated barns, and again, we look at stir fans and everything else in those units. It was decided to do this, but again, from an energy standpoint, the amount of electricity we have to use. These are 2-horse motors, so you can take 2 times 80. You're looking at 160 horsepower of fan power in that thing.